Hello everyone, welcome back to another GIS mathematics lecture video. And in this video we're going to continue our discussion on model and variable selection by talking about the Lagrange multiplier. So in the previous video we went through this idea of dredging and we came up with mu-min dredge, and we found that we had the top three models right here, and we see that we actually have our best model, including all of the variables here, with an ACIC of 829.6. And I actually misspoke in the previous video. Because this is the corrected AIC, this C here means corrected, we actually can trust that this is indeed the best model. We don't have to worry about that difference of 2 because we're accounting for that in the correction phase. So this right here, including all of our variables, is actually our best model. So we actually do have a little bit of confidence here that this model will work well going forward for us. So just to sort of recap with the summary of what we actually had here, right, is we actually have, this is the coefficients table, and you can see again, right, they're all mostly significant. And we can see that percent elderly and percent African American do seem to have the highest estimates. So there's that. So the next question then becomes, what do we do in terms of spatial, right? Because again, this is a spatial statistics class. We should probably be considering these things in the spatial context. And so how do we go about doing that? How do we incorporate spatial models? And so again, I'm going to talk through conceptually some of the stuff we talked about in previous videos, where I'm going to assume that once you've figured out that this is the model, that you would investigate, the correlation, the Moran's I, the spatially lagged means, and sort of maybe have an idea about what variables might have some spatial nature to them. But what I want to do is assume that you've done all of that, and I want to jump to this idea of the Lagrange multiplier. So Lagrange multipliers come from this SPDEP package. So if we do SPDEP : LM.LM tests. So if we run this, the Lagrange multiplier diagnostics for spatial dependency in linear models. So this is the Lagrange multiplier. And again, so what this is going to do is this is basically going to go through and it's going to do statistical checks for whether or not we have a statistical reason, again, to back up our intuition here, whether or not we should be running the spatially lagged X, the spatially lagged Y, or the spatial error model. And so what I want to do is I want to walk through what we're looking at here. So the LM.LM tests takes in as parameters model. So this is again going to be our ordinary least squares model, the one that we got coming out of dredge and all of that part of it. It also takes in this list W, which is our spatial weights matrix that we spent a lot of time talking about up before. And then this test here, this is going to say which test do we want to run. And what I'm going to do is I'm actually going to say for now we're just going to put all, and I would highly recommend just putting all there to begin with. And then when we actually run the code, I'll go through and explain what each test is showing us. So again, to recap, we need the OLS model, a spatial weights matrix, and then we need to tell it to run all of the tests. So what I want to do here is I want to actually go ahead and set up the code. So the first thing we need to do is take our model, which we have from OLS. I'm just going to copy and paste this down here just to sort of keep track of stuff, just to keep everything in the same place. Right, this is our OLS model. Nothing special there. The next thing we need to do is we need to create a spatial weights matrix. And again, if you're going through the steps in the way that I outlined them in the videos, you would have already had this because you would have done that spatial exploration in terms of looking at spatially lagged means and Moran's I. I didn't go through that here, so I have to actually recreate that. So what you do, just to sort of quickly do this, we're going to call this G and B. It's going to be equal to spdep colon poly to NB, PL equals GORGIA. Okay. And then we're going to, actually let's specify, I'm going to do this for the Rooks case. You don't have to, I'm just doing it for the Rooks case. And then GSW for spatial weights, spdep colon and B to list W. Neighbors is going to be our G and B. Run that. So we now have our spatial weights matrix, and then we're going to use this spatial weights matrix to run our LM tests. So we'll have LM for the Lagrange multiplier is going to equal spdep colon lm.lm tests. Again, takes in model, which is our OLS. It takes in list W, which is our spatial weights matrix, which is going to be our GSW for Georgia spatial weights. And then it's going to take in our test. Now, if you type all like that, right, if we scroll down here, right, test equals all computes all the tests. If we do that, if we run that, we don't get any errors. And then if we type in summary of LM, okay. So this is where we need to start thinking about the different models. So here, this is recapping what we did, right? We passed in our OLS model. Again, this is recapping the variables and what we did. This is telling us what data set we're using. This is telling us what we called the spatial weights matrix. And then down here, these are the statistic parameters. So LMER and LMER and LMLAG, these here are the same here and here, and LMLAG here and here. LM error, that is the spatial error model, and LMLAG, that is specifically the spatial Y, the lagged Y model. SARMA, we don't have to worry about SARMA. I would just say you can really ignore SARMA for all intents and purposes. Then this R LMER and this R LMLAG, these are what are called the robust Lagrange multipliers. Basically, you don't really have to worry about the difference between R and regular in terms of the calculations. Just know that these two account for things that aren't accounted for in the first two. So the way that I approach this is I approach this by looking at LMER and LMLAG first, checking the statistic parameters, checking the p-values. If one of these is significant and the other is not, you're done, right? Just take the one that's statistically significant. In this case, right, they're both statistically significant, right? This has a statistically significant p-value, and this has a statistically significant p-value, so then we can't just accept these. Then we have to move to the robust version, because again, the robust version is accounting for things that the regular version is not. So if we look at the robust version, right, again, check the parameters, check the p-values. Right, in this case, the literature suggests that you want to take the one with the better p-value. So they're both significant, so we move down to the robust. In the robust, we check and say, okay, which one of these has the better p-value? In this case, we're looking at the spatial error model, right? It has a better p-value, so we would proceed with the spatial error model, okay? So just to recap sort of what we've done over the course of all of this, right? We off video thought about our variables, right? Again, going based on Georgia, right? We thought about our variables. We did some exploratory data analysis. We looked at the relationships. We felt confident that we had a decent idea. We generated our first conceptual model here. Then we used dredge to confirm, right? Again, we just used this as a way to just sort of confirm our intuition that the models that we chose really was the best and that there wasn't some other combination that worked better. Then we used this LM tests, which is the Lagrange multiplier, to just explore and see if our spatial relationships mattered. Again, assuming that off video, we went through and looked at the relationships between Moran's eye and the different lagged means. And so finally, we ran the Lagrange multiplier test, and we got the results down here. And we look at the p-values for the first two. If one was significant and the other wasn't, we would have stopped. But because they're both significant, then we had to go down here to the robust versions. And we basically just picked the one with the better p-value, which is this one. So the results of all of this, right? So to sort of recap this in one sentence, the results of all of this are saying that the best model that we can come up with, given what we know for now, right? There's other things we haven't talked about, but given what we know now, the best model for this entire data set is going to be to model percent poverty relative to percent rural, percent elderly, percent African American, and median income included into this spatial error model. Okay, so hopefully you can see that workflow of how we got these variables, how we proved those variables were the best, and how we proved that using a spatial error model is the best alternative. If you have any questions, please reach out. Thank you.